Picking up from where we left off, we're talking about isotopes and how to calculate average atomic mass. So the first thing you need to know is that when we're talking about mass of atoms, we need a really small mass unit. And this is because atoms are so tiny that we can't just weigh an atom on the scale and see it read in grams. It's too small to weigh by itself. So we have a unit that we use just for when we're talking about things as tiny as atoms, and that's called AMU, or atomic mass units. And so the different steps that you would want to take for calculating your average atomic mass are, first, you want to divide percent abundance by 100, and that actually takes it from being percent abundance and makes it into a relative abundance. Second, you want to multiply your relative abundance, which you just calculated, by the mass of the isotope. And then third, and you do that for all isotopes, and that's true for step 1 too. Forgot that part. Okay, for step 3, you want to add all mass contributions together. And that gives you your average atomic mass. So I should say up here that this gives you your relative abundance. Running out of room. This step gives you your mass contribution. And this step gives you your average atomic mass. Oops. Atomic mass, which is what you're trying to find. Okay, so like I already said in the last video, average atomic mass is a weighted average, and that's why we use the abundances. However abundant an isotope is, it affects the overall average atomic mass. And the numbers you see for the masses on the periodic table, those decimal numbers, those come from there being more than one isotope averaged into the mass of the element, because more than one isotope exists for most elements on Earth. Alright, so element number 1. I'm calling it element number 1 because we can identify the element based on its mass if we know how to calculate the average atomic mass. So we're starting out with 2 different isotopes. I'll call them 1 and 2. Okay, and isotope 1 has 98.89% abundance and has a mass of 12 AMU. Isotope number 2 has 1.11% abundance and has a mass of 13 AMU. So if we wanted to find the relative abundance, well, I already wrote abundance. Oops. Okay, relative abundance, we could use what I said in step 1. Divide the percent abundance by 100. And I'm going to change that to abundances because we have more than one isotope. So that means I'm going to take 98.89%. I'll divide it by 100. That basically just cancels out my percent, and that gives me 0.9889. I'll do the same thing for my other isotope. I had 1.11%. I'll take 1.11%, divide by 100, and that gives me 0.0111. Okay, these are my 2 relative abundances. Okay, so then on the next step, I need to multiply the relative abundance by the mass of the isotope, and that will give me my mass contribution. So here I wrote mass contributions because I want us to find the mass contribution. So we'll take 0.9889, and just like it told us, relative abundance times the mass of that isotope, 12 AMU. And that will give us, I wrote this down earlier, 11.8668 AMU. Okay, then if we do the same thing for our other isotope, we have 0.0111 times 13 AMU. We end up with a mass contribution of 0.1443 AMU. To get the average atomic mass, all you have to do is add up your mass contributions, like it said up here in step 3. Add all mass contributions, and that gives you your average atomic mass. So if I add these two together, I get 12.0111 AMU. So that's my average atomic mass, 12.0111 AMU. And if you look at the periodic table, the closest element to this mass would be the element carbon. And hopefully you guys knew that, because in the last video I talked specifically about these two isotopes being the only naturally occurring isotopes of carbon. Okay, moving on to our second example. Element number 2. I'm putting this one in a word question, like a word problem, because a lot of the questions you guys will get will be word problems, especially throughout the course. And then we have to be able to find the important information. So an unknown element, if it's unknown, we're probably going to need to identify it, has 3 isotopes. Okay, so it says it has 3 isotopes. Then it says 2 of them are naturally occurring. So that means one of them is radioactive and doesn't exist in nature, really. The first one has a mass, so we'll call this isotope 1, has a mass of 1.0078 AMU. So that's the mass, and is 99.985% abundant. The second is more rare and has a mass of 2.0141 AMU and an abundance of 0.015%. What is the element identity and average atomic mass? So like I said, because it was unknown, we're probably going to have to identify it, which is exactly what it says down here. What, that's our question word, is the element identity and average atomic mass. So those are the 2 things we need to find. Okay, so like before, let's find our relative abundance. Let's take the percent abundance, so 99.985%, and we have to divide it by 100 to get the relative abundance, which will be 0.99985. We'll do the same thing for the other isotope. It was 0.015% abundant, so if we divide that by 100, its relative abundance is 0.00015. Okay, super tiny number. Alright, just looking at this, which one is more abundant, which one is going to affect our average atomic mass more? This is a bigger number, so this one should affect our average atomic mass more than this isotope. Okay? Alright, so let's calculate its mass contribution. So we need our relative abundance. That's 0.99985 times the mass of the isotope. If we go back up to the question, the mass of that isotope was 1.0078. And the mass we get for that mass contribution is 1.0076 AMU. Alright, the other isotope, we had a mass, or a relative abundance of 0.00015, and if you look back up in the question, it has a mass of 2.0141. So I'll write that down here, 2.0141 AMU. The mass contribution we get from that isotope is 0.000. Sorry about that, the lights just went out on me. Back to what I was saying, the mass contribution we get from the second isotope should be 0.00030 AMU. Okay. To find our average atomic mass, remember all we need to do is add these two things together, and when we add them we get 1.0079 AMU. And so that would be our average atomic mass, and we can check on the periodic table, and you should find that the element hydrogen is the closest element to that average atomic mass. And actually it's pretty much exact. So throughout this process we can calculate the average atomic mass by finding the contribution that each isotope gives to the overall mass, and then we can identify an element on the periodic table. And hopefully if you have any questions about any of these problems, you have written them down and will ask me or email me or whatever way you feel like you want to ask me a question. Alright, that's it for today.